Here we have an example in which we're trying to find the sine and cosine of 150 degrees. So the first question, what is the sine of 150 degrees? Basically, I want to show you two things. First off, I want to show you the unit circle and just how you will simply get answers for sine and cosine questions. So here it is. I'll be sending you a copy of this. Sine and cosine of 150, well, you just find 150 degrees right there on the unit circle. It's this dot right here. And the x-coordinate is the cosine and the y-coordinate is the sine. That goes for any angle around the entire unit circle. So the cosine of 150 degrees is negative root 3 over 2, and the sine of 150 degrees is a half. So we come up here and we say sine of 150 degrees, a half, cosine negative root 3 over 2. I think I got that right. Yep. So there we go. That simply answers the question. You'll be able to use the unit circle in your homework and on the exams. It's fine. You can use the unit circle and just look up the angles. So any angle they give you, if they asked us for the, let's say for 300 degrees, the cosine would be a half. The sine would be negative root 3 over 2. Notice cosine always comes first. That's all the way around. Cosine first, then sine. Cosine, then sine. Cosine is the x-coordinate. Sine is the y-coordinate. So all the way around the circle, the unit circle, whoop, I did that backwards. The unit circle here. The cosine is the x-coordinate, and the sine, whoops, is the y-coordinate. So there we go. So for pi over 3, 60 degrees, the cosine's a half, the sine's root 3 over 2. For 5 pi over 3, 300 degrees, the cosine's a half, the sine's negative root 3 over 2, etc. We can find any of those angles. Now for the other angles that are not listed here, like what about 20 degrees? We use our calculator. Simply for the ones not listed here, we use our calculator. Now, in the rest of this video, I want to give you logical reasons why that's true. I know some may not be interested in that and some may, so I put it at the end. So first off, to get these answers, just use the unit circle, find your spots. The x-coordinate is always cosine, the y-coordinate is sine. It's that simple. Now, how do we, where does this all come from? Well, let me first encourage you to think about two kinds of triangles. There is an equilateral triangle. So I'm giving the logic behind the unit circle. Like how they make the unit circle, where does it all come from? For those interested. So I'm making an equilateral triangle. All three sides are equal. Their length is 1. You can do that, right? You can just make a triangle any size you want. I'm saying make an equilateral triangle. All these sides are 1, and all the angles must be equal. Do you know that means they're all 60? Do you remember from geometry that there's always 180 degrees in every triangle? So if all three sides are equal, it's an equilateral triangle. Then all three angles have to be equal. So all angles and all sides are equal. The angles have to be 60. I made the sides 1. Now, why do I care so much about that? Well, now, let me go over here. And, oh, whoops. I didn't have my drawing tool. I thought, why did that come out looking so terrible? Didn't have my drawing tool. And that still came out looking pretty bad. There we go. All right, so that's supposed to be the same triangle. I'm not doing it very well, am I? It really looks different. That's just, I've got to get better. All right. Well, no, it's just terrible. There we go. All right. So each of these is 60. What I'm going to do is I'm going to split it. Well, you know what? After all that, well, that's right. I'm going to split it right down the middle. So this is 60. So this is 30 and 30. And if this goes straight down, here, let me try that again. I'm going to split it right down the middle. There we go. So that this is a 90-degree angle. This is still 60. This is 60. This is 30 because I broke the 60 straight down the middle, didn't I? And if that's going straight down the middle, this is going to be a half, and that's going to be a half, isn't it? This is still 1, and that's 1. Okay, why do I care so much about this? Well, now, let me get rid of this half of it, because I really don't care about that half. I just want you to see that. What is this? Call it y, call it Joe, whatever you want. You can find that y with the Pythagorean Theorem. Remember the Pythagorean Theorem? A squared plus b squared is c squared. The c has to be the 1, because it's the side across from the right angle. So a half squared plus the b is the y squared equals c squared. Or you could just call this b. Maybe I should call it b. It'd be easier, huh? Whatever. So this is a fourth plus b squared. Oh, and the c is 1. I forgot the c is 1. So 1 squared is just 1. So I'm showing you where these come from. Subtract a fourth. Boom. So b squared. What is 1 minus a fourth? Well, that's 4 fourths minus 1 fourth. That's 3 fourths. And then to solve for b, we root it. So b is the square root of 3 over the square root of 4. And what's the square root of 4? Whoops. It's the square root of 3 over 2. So this side must be the square root of 3 over 2. So we found a very important triangle. I just proved using that Pythagorean theorem, and by just splitting an equilateral triangle, I proved that the sides must be root 3 over 2, a half, and 1 for this particular triangle. Let me put a box around this thing because he's really important. And that wasn't a very good box. Okay, so there's one. Now, we're going to use that one, and I'm going to make another one for you. Let me go up here and do the other one. Pretty similar. I'm going to say, take a, here, let's do this. Yeah, I don't like that. Take a triangle. Oh, that was terrible. Take a triangle like this, where you make this side 1, and these both the same. So I made them the same. It's an isosceles triangle, that's called. This is a right angle here. And if these are the same, these must both be 45 degrees. Do you remember from geometry that if two sides are the same, if A and B are the same, well, in fact, let me just call it A and A, because they are the same. So I'm calling them by the same letter. So I made a triangle that has two angles the same, two sides the same. And so that means the angles must be 45 if this is a 90, because there's 180 total in a triangle. So what must those A's be? We'll use the Pythagorean theorem. A squared plus B squared is C squared. This is the C again. So this is A squared plus A squared is 1 squared. Now, you got to do a little algebra here. What's A squared plus A squared? It's 2A squared, and 1 squared is just 1. Okay, solve for A, divide by 2. Boom. So A squared is a half. How do we finish? Root it. So A is the square root of 1 over the square root of 2. Now we can't leave a root in the bottom. So we multiply top and bottom by root 2. A is, what is this? Root 1 times root 2 is just root 2. On the bottom, root 2 is root 4. Let me kind of keep this separate, which is 2, right? Plane 2. The square root of 4 leads to plane 2 on the bottom. So that means these two sides are both root 2 over plane 2, aren't they? That's what we just proved with that Pythagorean theorem, a little bit of geometry there. So I'm showing you the theory about where these come from. Let me make a box around this one now. So these two triangles become super important. We've proven the nature of two specific triangles. That is, when you have a triangle like this one with two 45-degree angles and the hypotenuse is 1, that root 2 over 2 is the measure of the other two sides. It's got to be. And we've proven that when you have the hypotenuse 1 and a 30 and a 60, that the sides are root 3 over 2 and a half. The one across from the 30 is the half. The one across from the 60 is the root 3 over 2. So we've proven those exist geometrically, and now that's where the unit circle stuff comes from. Basically, anytime you're across from a 30-degree angle, your distance is a half. If you're across from a 60, it's root 3 over 2. If you're across from a 45, it's root 2 over 2 when when your hypotenuse is 1. Your hypotenuse is 1. Let's go look at it. So that's what's going on with this unit circle. Let me try to erase these and show you what I'm talking about. So they used that truth to make the unit circle. They said, okay, say you're right here. Let's make a triangle out of that, starting from right here. I'm going to go straight over, straight up, straight down. There's my triangle. So this is some angle. Call it, well, I'll just call it angle. All right. And this is the x-coordinate. This is the y-coordinate. But notice they're saying 30 degrees. So this angle is actually, I shouldn't write angle, I should write 30 degrees. So 30-degree angle. And this is 1. So this is a, and if this is 90, because it's a right angle, it's straight up. So 180 in a triangle, this leaves 60. So what did we just see up here? About a 30, 60, 90 triangle right there. That across from the 30's the half and the 60's the root 3 over 2. So this is root 3 over 2, and this is a half when the hypotenuse is 1. Which means what? The x-coordinate is over root 3 over 2. That's why the x is over root 3 over 2. And it's up a half. That's how they're coming up with those coordinates. It's just a 30, 60, 90 triangle. That's all it is. And then they defined the cosine to be the x and the sine to be the y. Remember, that was made up. They literally just made that up. I don't know if you saw my other video on that. I want to be super clear. Sine and cosine were made up to describe, to be useful for things in the real world that are cyclical, that are periodic, that rise and fall, like pistons in an engine or blood in the human body or electricity coming out of a power plant, alternating current, rise and fall, or the orbits of the moon, and on you could go. Millions of things in the real world. Rise and fall, rise and fall, rise and fall. They're periodic, they're cyclical. And so they needed something in the math science world to make up that would fit the reality they were seeing in the real world. So sine and cosine are just made up. And they just said, hey, we'll just take a little dot and let it cruise around the outer edge of a circle. And anytime we stop, or right here, let's stop right here, the x-coordinate, we'll call that cosine of that angle we happen to be at. And the y-coordinate, the height, we'll call that sine of that angle we happen to be at. And then that thing will do a cycle for us, and anytime we're dealing with something in the real world that is cyclical, then we can use this sine and cosine to represent it with some alterations and stuff. And that's trigonometry. There you go. Sine and cosine made up to represent things in the real world that are cyclical. And here's how they made it up. They said the cosine is the x-coordinate and the sine is the y-coordinate. And they just put a bunch of 30, 60, 90 triangles. And then if you do the one right here, let me do this one. There's a 45, this angle here. Whoops, not very good. This angle here is 45 degrees. And so, therefore, this one is 2 because this is 90. So there's 45, 45, 90. So you know that's root 2 over 2, as we just proved up here. 45, 45, 90 triangle, right? 45, 45, 90. It's root 2 over 2 for those sides. When this is 1, again, why is it 1? Because it's a unit circle. See why we said unit circle? The radius is 1. The radius to that circle, which is the hypotenuse of all these triangles. So these are both root 2 over 2. That's where these values come from. And then in the other quadrants, we have negatives. If you go back and then up, for back and down, they're both negative, etc. That's how they got all these values, just using 30, 60, 90 triangles and 45, 45, 90 triangles, which we proved the numbers for up here using geometry. So that's sine and cosine. There's the values. That's how you do it.